Hey, great that you're watching this video. We'll be talking about some of our recent research, and we can just start directly with an example that you might know from your navigation system. Say you want to move from point A to point B, and the navigation system presents you with different alternatives. And on some days, you might want to take the path with the shortest travel time to get home quickly. On other days, you might want to minimize gas consumption. Or when you're on holiday, you might want to take the route with the nicest view. And in some situations, you might also have constraints on the route. Maybe you know that at certain locations, traffic jams are likely to occur, so you would want to avoid that. What we can see from this example is that your preferences might change over time. You might have different constraints in different situations. And the whole selection of what quality attributes are important can also change. And we've been developing an approach for the runtime adaptation of quality attributes in these automated planning contexts. My name is Rebekka Wohlrab, and my co-authors are Romulo, Meira-Góes, and Vierhauser. And to illustrate our approach, we can look at another example where automated planning is important. Let's say we have a robot in a warehouse that should move from a start location through the warehouse to pick up different items and then back to its start location. And there are different quality attributes of interest. One is the travel time, because the robot should get its job done quickly. Safety is also an important quality attribute, and that relates to collision avoidance. And there are certain path segments that are occluded or semi-occluded, and their collisions are more likely to occur. Privacy is another important quality attribute, and there are private and semi-private locations that should ideally be avoided, where humans might be and you don't want to intrude their privacy. If we look at these different options in the map, we can see that there are several potential policies. So one plan would be to go from the start location to location 2, 3, 6, and then back. And that would have a cost of 3.414 in terms of travel time. Safety would be 1, privacy would be 3, because it's a pretty bad policy in terms of privacy. In comparison to that, we have a policy via 4 and 5 that has a slightly lower travel time, higher safety, and 0 privacy cost. And now, if we look at these two policies, you might think, which one should I choose? Which policy is the optimal one for an automated planner? And that really depends on what quality attributes you think are important and what your priorities are. And we've been looking at ways to express what the priorities are and select the one that is optimal in the current situation. And your priorities there might also change over time. And similarly, you might have different constraints at different situations. And the question is, what constraints should an automated planner consider? Are there certain locations that should really be avoided, or can we allow any of these policies? What we can see is that both priorities and constraints might change at runtime. Human needs might change, the context of the system might change, and that's why we want to have an approach to adapt quality attributes. If we look at this example and think about how this would be expressed in a formal way, we can see that a lot of the times these quality attributes are expressed in utility functions. And the utility of a quality attribute is defined as 1 minus the cost divided by the maximum cost that can exist here. So in this example, 1 is the highest, the best utility, 0 is the lowest utility. For privacy, this policy here has the highest utility, 1, because it's far away from the worst cost. And that means it's really good in terms of privacy, but pretty bad in terms of safety. So the concrete utility values here would be 0.113 for time, 0 for safety, 1 for privacy, and that really means what the usefulness of this policy is and can help people select one policy over another. If we have the utility values of different quality dimensions, we want to bring that together to the overall utility of a policy. And there we often express that as a weighted sum. So as an example, we can see that this would be the weight times the utility of a certain quality dimension, and then we sum that up for these different quality attributes. So here, if we take 1/3 for each, it would look something like this. And in that case, actually, the one via 4 and 5 is the most optimal. But if we have a utility function that really prioritizes safety, then this would be pretty bad for the policy via 4 and 5 and would likely end up with a very low utility value. So this is the way it is often expressed in automated planners, and in previous research we've been looking at ways to elicit what the utility function weights should be by asking people questions and capturing their priorities. And if we look at the literature here, we can see that utility functions in this way with the weighted sum are very common and have been used a lot in the past. But a lot of the times people have neglected the question of how utility functions should be adapted over time. And that's something we want to address in this paper, along with adaptation of constraints. If we look at that issue a bit more in detail, what we have for these different policies to capture quality attributes is on one hand the utility function, and then we can have a variety of constraints. One might be that we have bounding measures constraints that say we really have to get this job done within 3.5 minutes. And there we can bind the costs of different quality attributes. Proximity constraints are another example, so that we can express that a robot must not be within 20 meters of a human. And we can also express constraints like speed limit constraints due to safety regulations and bring them together, and with that filter out the policies that are feasible, that fulfill our constraints, and then select the most optimal one based on utility functions. And as I said before, in the examples we talked about, all of these things might change over time. So one thing that can happen is that the map changes and that locations become unavailable, or that the task changes and all of a sudden the robot should transport a vulnerable item, and that might mean that we really don't want to have any collisions. Stakeholder preferences might change, and humans say, no, this is more important than that one. And we could also have regulatory changes, for instance, with respect to safety regulations, and that would impact our constraints. So we've been developing an approach that supports this runtime adaptation of quality attributes. And now I will go through the main components of the approach and how they are connected to each other. The basic idea is that human stakeholders can interact with a quality attribute configurator and indicate their preferences and their constraints and access a knowledge base in which all information is stored in this approach. That information is then sent to a quality attribute adapter that takes the information from the knowledge base, processes it, and that can also be supported by a reasoning engine. So in certain situations, we have several constraints that all have to be consolidated with each other. We might have humans with different preferences and want to consolidate that information as well. And there it's useful to use a reasoning engine, and I will show you a bit later what that can look like. But there are some situations in which conflicts might occur between constraints that just can't be consolidated with each other. And then, if needed, we can solicit human input and point them to resolve constraints. Based on this information from the quality attribute adapter, a utility function is generated and a set of constraints that should hold. And they are being sent to a model creator that can create a Markov decision process to express the automated planning problem, and also PCTL properties that are used by a policy synthesizer to find out what the optimal plan is. So these are the components that are important for the automated planning part. And in this case, we focused on Prism as a policy synthesizer, but it could also be replaced with other automated planners. I will show you a bit later what these steps actually look like in detail. What is important here is that the policy synthesizer outputs a policy that the robot can then use to do its tasks and collect runtime data based on sensors and whatever is going on in the environment of the robot and the costs of this policy. And all of that is fed back into the knowledge base and can then also be visualized to a user who is interested in what is going on at runtime. There are several things here that might change at runtime and where changes would lead to new triggers of the quality attribute adapter and new needs to create models and synthesize policies. So one example is that humans change or add input, new constraints, or change preferences. Another example is that tasks might change, and that requires a redesign of utility functions. The environment might change with the map and maybe locations becoming unavailable. And all of these changes might trigger iterations of this approach. And some things can be done without the human being directly involved, and some things are involving humans and maybe being triggered by humans. I told you that I would explain this model creator and policy synthesizer part a bit more in detail so that you get an idea of what that looks like. And here we can see that for this part, we express such a planning problem as an MDP model, so a Markov decision process, and that is then encoded in Prism in this example. And that looks like this. So here we have a screenshot from the tool called Prism, where we can see the reward structures in terms of time cost, collision cost, and intrusiveness cost. And then we also see that the utility functions are being embedded in this Markov decision process. So for the utility weights here, we have 0.3, 0.4, 0.3 in the example, and that is all factored in the overall cost of the system. In this example, we also have a constraint where location 5 becomes unavailable because a human is entering the map at that location, and that would then be captured in a PCTL property, which is used to generate the policy that the system should use. And in this case, it is defined as a multi-objective goal that tries to minimize the overall cost, and then with a probability of at least 1, so it's really ensuring this, it calculates the policies in which the robot ends up at location 6 and never visits location 5. And that is how we enable this constraint to be fulfilled so that all policies which will be output by this planner avoid location 5, and that is captured in this PCTL property. As an example for the reasoning engine that the quality attribute adapter works with, we can look at a rule that this reasoning engine rules uses to resolve conflicts between constraints. That only works if we're considering soft constraints here. For hard constraints, we probably need to solicit human input. In this example, we have one constraint that is a lower bound constraint that is in conflict with another constraint being an upper bound constraint. And then the values are so that the two constraints cannot be fulfilled at once. In this example here, we could have a constraint that says the travel time should be larger than 5, and another constraint that says it should be less than 4. So both of them cannot be fulfilled at the same time. And the way to resolve this is to create a new constraint that takes the mean of these two travel time values, sets it to 4.5 in this example, inserts that into the knowledge base, and adds conflict traces. And with that, we can generate constraints that can then be used for the automated planner to create policies. It's not always the way these constraints should be consolidated and conflicts should be resolved, but ideally we want to have different strategies depending on the context and what kinds of constraints we're dealing with. But this was one example how a reasoning engine can deal with conflicts. For the evaluation of this approach, we've been doing an initial way of looking at scenarios in which, on one hand, utility weights are equal, 1/3 for each quality attribute, one in which we have a scenario where a valuable or dangerous item should be transported. That means that the importance of safety is increased, and that's 0.9 in this case. The travel time priority is 0.1 and the weight of privacy is 0. And that means, of course, that the policy is likely to be different and tries to avoid more of these safety critical paths in which the safety cost is high. And then we have a third scenario in which an added constraint has to be considered, in this case that a location becomes unavailable because a human is entering the map. And we're looking at what the calculated utility values will be in the case of no adaptation versus in the case in which we use the system to adapt quality attributes at runtime. And then for these different scenarios, you can see the details in the paper. We calculated which policy is optimal of these three that we have here and what is its utility value. And what we can see here is that if we have these different scenarios, if we adapt the utility function, then the version with adaptation leads to a much higher utility value than the one that doesn't have adaptation, just relies on stable utility function weights. And then for adapting a constraint and adapting both the utility function and constraint, we have similar outcomes, that the value of not using adaptation is much lower than if we use this quality attribute adaptation framework. And for the next step, we actually want to evaluate this further and also experiment with different types of constraints and preference representations. While it's very common that these utility functions are defined with the weighted sum approach in practice, there are also other mechanisms to represent preferences and to capture constraints. For instance, time-bound constraints would be interesting to explore, and hard and soft constraints. And we also want to work with different contexts in which different preferences are needed and different constraints are important, and ways to elicit that information from stakeholders without overwhelming them with too many questions about too many potential contexts. For all of these things, it's crucial for us to have good mechanisms for stakeholder input and explainability, so that humans who use this quality attribute configurator can see what's going on and give their input for preferences and constraints. And we also want to evaluate this with realistic systems and conduct think aloud studies to see how humans reason about quality attributes and can work with this framework. Thank you very much for listening to this talk, and feel free to contact us via email if you have any questions.